So this is a mass spectrometer like example problem. This is not one from page 21. This is just one I wrote up, but the ones on 21, they kind of like focus on different parts of the mass spectrometer, like the accelerator, selector, the detector. This is kind of all of it in one problem. So hopefully it'll kind of help you, understand how to solve these kind of problems. So a company is going to determine the mass of a neutron by sending a deuterium nucleus through a mass spectrometer, which is one proton and one neutron. So first, they accelerate the nucleus through a certain potential difference. So just as a refresher for what a mass spectrometer is, right, we have the accelerator, which is going to accelerate this thing, our nucleus, and then there's going to be a selector, right? And this is also going to have, so if there's, positives here as well. And finally, after the whole accelerator and selector, it's going to go through the detector, which is when it's going to go in uniform circular motion, because if you think about the velocity, right, it's always going to be so the magnetic force is always going to be perpendicular to your velocity, and that's a right-hand rule kind of statement. So it's going to go through circular motion and eventually crash into the walls or something. So I should finish the problem. Afterwards, the nucleus travels through two parallel plates that are separated a distance of 30 meters, and a potential difference of 300 volts exists between the plates. So to keep the nucleus from deflecting into a plate, a magnetic field of 50 millitesla exists pointing into the page. So hopefully it makes sense why it's pointing into the page, because if we use our right-hand rule, the electric field points downwards and it's positively charged, the nucleus, so it's gonna have a force downwards, the electric force. So we need a magnetic force to kind of balance it out. So it has to point into the page, because if you use your right-hand rule, to get an upward force, the magnetic field has to point into the page. So what is the selected velocity from this process? So there's a shortcut equation, but if you don't know what that shortcut equation is, to solve this problem, you just set the magnetic force equal to the electric force, because everything has to balance out when it's going through this thing, like I just explained. So QVB is equal to Q and then E. So this is the equation for magnetic force, equation for electric force. Q's drop out, and you get pretty simply that the velocity is going to equal, or I guess speed technically, E over B. So the electric field over the magnetic field. We know the magnetic field, but we don't know the electric field, but that's okay, because we know the voltage across the plates, and we know the distance of separation. So we know that V is equal to voltage, by the way, so big V. I'll just try to make this one big to make it different. Big V voltage is equal to the electric field times the distance of separation for parallel plates. So I can solve for E if I know the voltage is 300 volts and the distance of separation is 30 millimeters. Cool little side note, by the way, milli means 10 to the negative third. I know I always forget, like, how do I convert millimeters to meters or whatever. You can just write 30 times 10 to the negative third meters, and that's on your equation sheet. If you forget it, maybe I'll if you can ask me and I'll explain more about that. 300 over 30 times 10 to the third, you get let me just plug this in my calculator. I think it's 10,000. Could be 10,000. I think it is 10,000. Yeah, you get 10,000 voltmeters, newtons per coulomb, whatever you want to call it. So now we can plug this back in here. Velocity is equal to 10,000 newtons per coulomb over the magnetic field is 50, right, times 10 to the negative third, right, because it's milli. And that should get you, I think, 200,000 or something crazy. Yeah, 200,000, or V is equal to 2 times 10 to the fifth. meters per second. Cool. After leaving the selector, the nucleus is traveling in the positive x direction while entering a 50 millitesla magnetic field in the positive z direction. So just as a reminder, if we think about our axes, x direction, right, this would be the negative x, this is y, this would be negative y. Positive z is pointing into the page, and then negative z is pointing out of the page. So it would look, if we go back here, our picture would actually look a little bit different. It would look like this. It would be pointing out of the page. So 50 millitesla again, though. The radius of the resulting path is measured to be 8.35 centimeters. Determine the mass of a neutron. Which is kind of cool, right? Like, you can use this information and, like, determine the mass of, like, the most fundamental, like, smallest units. Actually, probably, like, I know there's quarks. I don't know quantum mechanics, but it would, I think it's kind of cool that you can figure this stuff out with a mass spectrometer. So let's, it's going to move in circular motion, uniform circular motion, because the force is always perpendicular to velocity by a right-hand rule. So there's going to be a centripetal net force, which is going to equal to mass times the centripetal acceleration. The net force on the nucleus is the magnetic force, and the centripetal acceleration is v squared over r. So the magnetic force is equal to qv times b, and then mv squared over r. One of the v's drop, so I can actually just do it like that. So I get qb is equal to mv over r. So what I can do to solve for m, we're going to isolate it, and we're going to multiply both sides by r, and then divide by v to get rid of the v's and r. So I get qbr over v is equal to m. And we know all this stuff, right? This is actually not that bad, because I can just say the charge, right? It's just one proton. Neutron doesn't have charge. We're just going to hope the scientists know that. 1.6 times 10 to the negative 19 coulombs. The magnetic field is 50 times 10 to the negative third Tesla. The radius is 8.35 centimeters. That's kind of easy to convert, but it's actually the same thing. You can do 10 to the negative 2. Let me move this over. 10 to the negative 2 meters, because centi means like 10 to the negative 2. Same way how micro means 10 to the negative 6. And then we're going to divide all of that by the velocity, which we found was 2 times 10 to the 5th meters per second. That's going to equal your mass. So you should get that the mass is equal to, when you plug this onto your calculator, I'm just going to do it really quickly, 1.6 times 10 to the negative 19 times 50 times 10. Sorry for my parents, by the way. They're calling people because it's actually like a New Year's for us, like in our culture. Times 8.35 times 10 to the negative second. Divide that by 200,000. You get I messed up somewhere. I think I got 3.34 times 10 to the negative 27 kilograms. Now, this is the mass of the deuterium like nucleus, right? I solved the mass for the whole thing, but I want to find the mass of a neutron. Well, that's pretty easy. I can just subtract by the mass of the proton, which is given to be 1.67 times 10 to the negative 27 kilograms. And I get the mass of a neutron is equal to I actually just get 1.67 times 10 to the negative 27 kilograms. So you can actually check your equation sheet. This is actually the mass of a neutron. So now the scientists know the mass of deuterium and many other isotopes. Going back to the scenario from part A, determine the potential difference that the deuterium nucleus was accelerated through. So this part was about the selector, right? This part B was about the detector, but now we're going back to the accelerator. So if we think about the accelerator, there's gonna be a certain potential difference that it is accelerated through. And then I can use that to find the potential difference. So I can use conservation of energy here. How do I know to use conservation of energy? It's like an electrostatics concept, and when you're dealing with like things being accelerated, like you could use kinematics, because there is like a uniform electric field, but energy just makes it kind of easier. So and then you can use the electric field to find out the electric force divided by mass, get the acceleration. And then you can kind of go you don't really know distance, so I guess you kind of have to use energy here because you don't know the distance traveled. So UE initial is going to equal, I could say UE initial is going to equal K plus UE final, but really it's going to be change in the electrical energy is going to equal the change in kinetic energy, right? Because that's a conservation of energy statement. Whatever your change in electrical energy is, you find that in your kinetic energy. So what I can do now is, What I can do now is say, okay, Q times change in V is going to equal 1/2 mv squared. So change in V, well, I guess I could just really quickly plug things in. 1.6 times 10 to the negative 19th coulombs. Change in V is going to equal 1/2. The mass was 3.34 times 10 to the negative 27th kilograms, and then multiply that by 2 times 10 to the 5th meters per second squared. And then you can solve for change in V. I'm going to really quickly do that. Okay, 0.5 times 2.34 times 10 to the negative 27th times 2 times 10 to the 5th squared. Divide that by 1.6 times 10 to the negative 19th. You get 417.5 volts. So yeah, thank you for listening. Hopefully you can now try page 21. These three are kind of the main big concepts that the thing asks you on. All right, bye. My dad's about to yell at my brother for sleeping in.